Good afternoon, everyone. We'll just do a couple minutes of informal hellos before we get started with Carl's presentation. So anyone who wants to say hello, go ahead and say hi.
I think we're all excited to hear the presentations.
I think so. We sure are. Well, we have two speakers today. So the first is Carl Luetzelschwab, K9LA. He's going to talk about ionospheric ray tracing, and he's very well known for his propagation writing and work. And then after that, we'll have Veronica, KD2UHN. She's a undergraduate student who's been working with me here at the University of Scranton, and she will be joining us a little bit later because she's in class right now. So she has to get out of one Zoom class, and then she said she'd be able to join us starting around like 3:20, 3:30. So why don't I go ahead and, let's see, Carl, I'm gonna make you a co-host, and then you can go ahead and share your screen. So take it away, Carl.
Okay, well, hello to everyone. And well, here in Northeast Indiana, it looks like winter's coming. It's about in the around 60 today and windy and cloudy. So, well, that's the way it goes here. Let me, let's see here. A little more. Okay. Let's see here. Stop recording now. Okay, oh, there's the share screen finally showed up for some reason. I don't know why, but it did. So let's wait for that. Yeah, I emailed Nathaniel, I guess it was 2 weeks ago, and offered to do this. I told him it's going to be kind of short, and it is. Hopefully it's getting there. You put it in the presentation mode. That usually, for some reason, usually takes 2 shots until that happens. Ah, there we go. At least I can see it in full presentation mode.
Yeah, it looks good here too, Carl.
Okay. So I'm Carl, K9LA, Northeast Indiana, Fort Wayne. And I'll talk about HF ray tracing, talk just a little bit about historical ray tracing software, because there's been some stuff before what's out there now. A review of the currently available ray tracing software, and there's only 2 programs that I'm aware of that really probably fit the bill for us. And I'll show some interesting ray trace examples. So let's get started here. What ray tracing is it's a great visual aid to supplement tabular data. Especially the 3D ray tracing can give a truer picture of propagation. And we'll see that in a little bit here when we talk about what the various programs can do and show some examples. Now this kind of started from the Taper Digital Communications Conference on September 11th, and Steve, WA5FRF, showed a ray trace for his WWV to his QTH on a January day at 1430 UTC. This is a 2-dimensional ray trace. In other words, it only traces in the plane of the Great Circle path. It doesn't allow skewed paths due to horizontal gradients. And the ray trace went from 4 to 50 degrees in 1 degree steps. You can see things get very crowded there. The red traces, the red are the ordinary wave. And what's highlighted in green are the 5 modes that arrive at WA5FRF on that January day at 1430 UTC. There's a 1-hop E mode, there's a 2-hop E mode, there's a 1-hop F mode, there's a 2-hop F mode, and a 3-hop F mode. So things can get complicated pretty quick. The ray tracing software allows you to determine the phase or the delay, so you can generally sort out what you're receiving. And this came from PropLab Pro, one of the current ray traced programs. Now, I started ray tracing many years ago, in fact, in the mid 1990s. And Bob, NM7M, who was a silent T, he was a professor at the University of, at Berkeley in physics. And he wrote a program called PrettyBird.Basic. And he was doing ray traces from satellites to ground level. Now, about that time, I ran into Gus, K2ARO. He had 2 solar cycles worth of 10-meter long path contacts. And that was great. So Gus and I took the PrettyBird contest, PrettyBird program, and modified it for ionospheric ray tracing. And I used that in a 10-meter long path article in the ARRL Compendium Volume 4 in 1995. Now that ray tracing was very simple and very manually intensive. It was only a 2D program. You can only ray trace in the plane of the Great Circle Path. Now what you needed to do was determine the E region critical frequency, the F2 region critical frequency, and the height of the peak electron density in the F2 region all along the path. Take that data, do some curve fits to get equations, and then insert those equations into the program. So it was very manually intensive, but you sure learned a lot about the ionosphere and other stuff. Now, the next program that I'm aware of, at least in recent times, is Chris Coleman, VK5 Alpha Hotel Zulu. I think he's a member of the HamSCI. I'm not sure about that, though. And he used his earlier developed ray tracing program from 1993 in his 2002 paper in Radio Science, when he looked at the direction-sensitive model of atmospheric noise and its application to the analysis of HF receiving intent. I kind of think that Chris's program is some of the roots for FARLAP. Nathaniel has commented that maybe the 3D option in FARLAP is something different. And
do you mind if I chime in, or are we going to let the
not at all
presentation go? So I think the FARLAP's programming has its roots actually in the original Jones-Stevenson code. It's just it's done in Cartesian coordinates as opposed to spherical coordinates, which is what Jones-Stevenson did.
No, that's the 3D code, but the 2D is definitely Chris Coleman's.
Yes.
Yeah.
Okay.
So FARLAP has a 2D and a 3D code. The 2D is Chris Coleman's, and the 3D is Jones and Stevenson.
Oh, cool. Okay.
Great. Okay. Well, thank you for that comment. I can make some changes to this slide and get it correct. Interestingly, back in the late 1920s and the early 1930s, there was a champion racehorse in Australia named FARLAP. And I kind of wonder if there's some kind of tie here, because some ionospheric physicists have a pretty unique sense of humor here. So we'll just leave that. And here's a slide about FARLAP. It's from the Department of Defense of the Australian government. There's the acronym. It's a MATLAB toolbox. It does, like was said, it does 2D and 3D ray tracing. The 3D also includes the magnetic field and electron neutral collisions, so you can calculate the absorption in dB. And of course, 3D can show skewed paths due to horizontal gradients in the ionosphere, and that's pretty helpful. It also gives polarization. It uses the 2016 version of the International Reference Ionosphere. But one of the big advantages of FARLAP is you can input other ionosphere models. Now here I listed two examples of people using FARLAP. One is Peterick and Cervera. Used it in their direction noise model in radio science in, let's see, that'd be 2015, I guess. And then Nathaniel and others used FARLAP in their modeling amateur radio soundings of the ionospheric response to the 2017 Great American Eclipse. And what they did is they input an eclipsed SAMI 3 ionospheric model. So that's kind of neat that you can do that. Now, I'm not saying it's simple, and I think maybe Nathaniel might agree with that. But I guess once you start using FARLAP and do it a lot, I guess it gets simpler and you get used to it. So FARLAP is pretty good. Now, what I'm most familiar with is PropLab Pro. It's offered by Solar Terrestrial Dispatch in Canada, Kerry Oler. He's out of Stanford. Unfortunately, his support for PropLab Pro recently doesn't seem to be too good, but that just means you have to dig deeper to try and understand any issues you need to resolve. Originally, it came out as SkyCam version 1 in '93, but there was already a propagation prediction program called SkyCom. So Solar Terrestrial Dispatch changed SkyCom to PropLab Pro. PropLab Pro version 2 was in '94. It was a DOS program. That was a lot of fun. It used the 1995 version of the International Reference Ionosphere. Lots of manual inputs required to do a ray trace. But that was a great way to learn about the ionosphere. Then in 2008, PropLab Pro version 3 came out. It was a Windows program, and it uses the 2007 version of the International Reference Ionosphere. That's the only option you have as far as I understand. Now it is, the Windows version is very user-friendly. I'd probably say it's more user-friendly than FARLAP, but the ability to put in different ionosphere models can be very useful at times. Now, since it's so user-friendly, you don't have to know as much, and I don't know if that's good or bad. I can think of both good and bad reasons there. It also does 2D and 3D ray traces. It gives polarization. The format in the version 3, the Windows version, is confusing though. So if I'm looking at polarization, I usually use the DOS version 2 because it's very understandable. And PropLab, the roots of PropLab are from Jones and Stevenson Fortran program in '75, which we discussed earlier in relation to Chris Coleman's stuff. So let's look at some examples. Here's a very simple one for a moderate solar activity, nighttime, about midnight. And it's the distance and height versus frequency. Now, all this data, of course, would come out of a tabular run, you know, like with VOACAP or something, or W6EL prop. But boy, the ray trace visually shows you much better what's going on. And as you can see, the lower the frequency, the shorter the hops, and the ray doesn't get as high into the ionosphere. So that's very interesting to know. In fact, you can see down at 0.15 megahertz, which is kind of close to our 2200 meter band. The ray hardly gets up into the, it doesn't get very high into the ionosphere. And that can kind of lead you to conclude why Loran C was down at 100 kilohertz, because it was not affected as much by geomagnetic field conditions and other, you know, flares and all that kind of stuff. So this is good to know that the lower the frequency, the shorter the hops. Here's another example. This is 160 meters. Trying to understand 160 can be very difficult, and ray tracing can help, but we certainly don't know everything about propagation on 160 meters. This ray traces at night on 1.82 megahertz. The ray traces are from 9 degrees to 24 degrees in 3-degree steps. And what you can see is there's three categories of modes. Up to 15 degrees, you get EHOPs, which are kind of short, probably a maximum out to 2,000 kilometers for very low angle stuff. And then in the range of about 15 to 21 degrees for this Raytrace scenario, 15 to 21 degrees elevation angle, you get ducting in the nighttime electron density valley above the E region peak. We'll talk about that a little bit later. And above 21, then we resort to FHOPs. Now, one thing that I've always wondered about are EHOPs good for 160 meter propagation? I think if you live near salt water, they might be good, but other than that, well, I'm not too sure. Another example, gray line propagation. Hold on, I think that might be Vicky. Hello. No, come on home, okay? Come on home. Come on home. Okay, bye. Okay, that was Vicky. She just got off work, so okay. So here's gray line propagation, and what gray line is that's when the great circle paths align with the terminator, and that's what this picture shows. And this is from the mapping feature in W6EL prop. You can easily see the daylight and the dark and the night side of the ionosphere. The path is from my QTH in Fort Wayne to India on February 15th. Bob, yes? WK2Y raised his hand if he'd like to ask a question. It's fine with me.
There we go.
Okay.
Sorry, took me a moment to unmute.
Yeah. Oh, yeah.
Pardon the question. What is a terminator?
Okay, the terminator is the division between day and night in the ionosphere.
Oh.
It's usually considered to be a sharp distinction, but it really isn't.
Is it different than the gray line?
Well, I think those two words are synonymous.
Okay.
Gray line and terminator. Terminator, I think, is more the astronomical term of between day and night, whereas gray line is kind of ham radio-ish.
Okay.
So what we have here is a very classic gray line propagation scenario. And gray line is claimed to be very efficient on the lower bands, 160 and 80, and that comes from some measurements by some W6s on the long path on 75 meters to Europe back in the 70s. And they noted that their antennas were kind of pointed along the terminator. So they assumed that propagation was very efficient, and that has grown into pretty much a universal, yeah, that's what it is. But let's take a look at a ray trace along the K9LA to VU path on the long path. It's to the south. Note that the dark ionosphere is on the right as we're going from K9LA towards VU on the long path. So the dark ionosphere is on the right, daylight's on the left. So let's do a ray trace on 160. And here's one way to look at it. This is looking side view of the path. It's at a 15-degree elevation angle. You can see where K9LA starts. Now, after about 4,000 kilometers, the ray is skewed to the right, okay? And there's about 172 dB of absorption after 4,000 kilometers. So that's prohibitive on 160 when you do some math with the free space path loss, antenna gains, power, etc., and typical noise levels. Now, when you do the extraordinary wave, and we'll get into that a little bit later too, the absorption is significantly higher, it's about 600 dB after that 4,000 kilometers. And it's due to 160 meters being close to the electron gyro frequency. which is around 1 to 1.4 megahertz worldwide. It can get lower and can get a little bit higher too. So here's a picture looking along the path. And what this shows is the skewing to the right much more, it's much more visual. Again, the dark ionosphere is on the right. We're looking south from my QTH. And you can see the RF just can't follow the terminator. And why does it do that? Because there's a lot more there are many more electrons on the daylight side of the ionosphere, and there are a lot less electrons on the dark side of the ionosphere. So electromagnetic wave is going to bend or refract from the higher electron density towards the lower electron density, and that's what it's doing. And what the conclusion is 160 meter RF has a tough time following the terminator due to the electron density gradient across the terminator. And also the absorption is just prohibitive. One of the explanations of gray line has always been that, well, the D region goes away right along the terminator. Well, that's not really true. And that's another story for another day. There is an alternative explanation for gray line propagation, but that's, like I said, that's for another day. So there's another interesting phenomenon in 160, it's ducting. During the night, an electron density valley can form above the E region peak in the nighttime ionosphere. Chapman theory predicts the valley, and rocket flights and incoherent scatter radar measurements confirm its presence. And there's a picture on the left there of what that valley looks like. You're looking along the path, and that's the electron density profile. You can see the E region peak around 100 kilometers. You can see the F2 region peak around, looks like about 250 kilometers. And there's a valley that, if you kind of think about it, the 160 meter RF can refract from the top of the E region peak, the top of the E region, between the top of the E region and the lower F region. So there's a ray trace of ducting on 160. Now that comes from the DOS version because it's a great example. This ray trace is from Sudan to K9LA, and you can see the ray gets into that valley and ducts. Now what that does is it avoids transits through the D region, the absorbing region. It avoids ground reflection losses. And the only issue is how does it come out of the duct? Well, more than likely it's due to irregularities in the F2 region or the E region. And that's how it gets dumped out of the duct. Now, Brown NM7M investigated ducting in relation to magnetoionic theory. And he found that ducting on 160 is more prevalent for quasi-longitudinal paths. In other words, paths that are kind of more aligned with the magnetic field as opposed to going across it. And that ducting can be non-reciprocal. In other words, you may enter the duct from one end of the path, but you may not be able to do that from the other end, and that could make the path very non-reciprocal. Interesting stuff, a lot more that could be looked at too. Okay, the ordinary and the extraordinary wave. This came from Bill Lyles, NQ6Z, asked about if I'd show a good example of the difference between the ordinary and the extraordinary wave. And here's a little picture of kind of what happens is when we send our RF up to the ionosphere, whatever polarization we're using, I show a horizontal Yagi in this figure. The polarization is constant until it enters the bottom of the ionosphere, which is the lower D region. When it enters the ionosphere, it couples, all that energy couples into the two characteristic waves that propagate through the ionosphere. And they're called the ordinary and the extraordinary wave. Now, how much power goes into the O wave and the X wave depends on the polarization match between the horizontal transmit antenna that I show and the polarization of the O wave and the X wave at the entry point. Again, FarLab and PropLab can tell you what the polarization of both of those characteristic waves are at the entry point of the ionosphere. And from that, you can calculate how much energy goes into the O wave and how much goes into the X wave. So the O wave and the X wave propagate through the ionosphere, and eventually they come out at the receive end. Again, PropLab and FarLab can tell you what the polarization of those two characteristic waves are when they exit the ionosphere. And from the bottom of the ionosphere to the receive antenna, those polarizations are constant, and you can calculate which the O wave or the X wave will put more energy into the, for example, this quarter wave vertical that I used. You know, what doesn't matter what happens to polarization as the wave goes through the ionosphere. The only thing that matters really is what's the polarization at the entry point for both the O wave and the X wave, and what's the polarization when it exits the ionosphere. And knowing that, we can determine what the polarization match is between our antennas. Pretty interesting stuff, and it can get quite complicated, so whatever. So here's a picture on 10 meters of the O wave and the X wave, and you can see they propagate the same, well, essentially the same. The refraction and absorption is pretty much equal for both the O wave and the X wave. But then when we move down to 160 meters, which is close to the electron gyro frequency, refraction can be significantly different, and it shows. The red is the ordinary wave, green is the extraordinary wave. And the absorption is significantly higher for the X wave. And that was seen on slide 9. And again, that's due to the 160 meters being close to the electron gyro frequency, which is the frequency at which those free electrons spiral about magnetic field lines. Pretty interesting stuff. And, you know, if not having ray tracing, you wouldn't see what's going on. Now, all this doesn't explain everything, but at least it gives you some ideas. So, in summary, here's some things that still, you know, can be done. If the model of the ionosphere in your ray tracing program is a monthly median model, like, you know, the International Reference Ionosphere, then your results are monthly medians. They are not daily results. And the only way to get daily results is to use a daily model of the ionosphere. The equivalent sunspot number gets you a little bit closer to a daily ray trace, but it's not perfect. What is the equivalent sunspot number, SSNE? Well, that's when you take a model of the ionosphere, of the F2 region of the ionosphere, and vary the sunspot number so that FO, F2 values match ionosan data at the time you're looking. The ionosphere is very dynamic. You won't get a perfect match, but it's a little bit closer. Now, I think what's really going to help is the International Reference Ionosphere people. That's the COSPAR and the other group. What's the other group? COSPAR and
URSI?
Yeah, URSI, URSI. Yeah, they're working on assimilating real-time ionosonde and tech data into the International Reference Ionosphere. So hopefully that'll get us much, much closer to a daily model. And then we can really, I think, gain some more insight into what's going on in the real ionosphere as it varies. PropLab and FarLab do not address scatter. Scatter is the likely explanation for the above the MUF mode. In other words, normally we think of propagation does not occur between point A and point B if the MUF is lower than the operating frequency, but observations, real measurements show that it still happens, and it kind of appears to be due to scatter. We can't do scatter unless somebody can think of a model of the ionosphere that addresses that. Well, I think it's more than the model of the ionosphere. It's probably the actual, the Appleton-Hartree equations and all that kind of stuff. Now, PropLab and FarLab do not address sporadic E. But it seems to me that Nathaniel kind of asked me this question and piqued my interest a little bit. We know a lot about the statistical pattern of sporadic E, and if we can make a monthly median model out of it, you could import it into FarLab, and you could probably do some ray tracing for the summer months with sporadic E. Interesting thing to think about. Now, in summary, ray tracing is just another tool to try and figure out what's going on. And of course, it allows you to visually see what happens, and it can make more sense than a whole bunch of tabular data. So that's all I had, Nathaniel. Any other questions I can try and answer?
Thank you very much, Carl. That was a great overview.
Yeah, that's what it was intended to be, a very broad overview.
I see other people with PhDs in ionospheric physics and ray tracing expertise are putting comments in the chat window saying very nice presentation. So thank you, Dr. Kepler. So yeah, any questions for Carl?
Yes, Carl, this is Tom. Are any of these ray trace tools available publicly, or they all require purchase? What's the status?
Okay, well, PropLab you can buy from Solar Terrestrial Dispatch. I think it's somewhere around $300, $350, something like that. It's open to the public. Comes with a decent manual, although there's some issues there. FarLab, I think it's free, isn't it, Nathaniel? You just have
it's free. Yeah, you just have to go online and you go to their website, which we can put that link in the chat in a minute, and you can fill out a form and you download it. And so that is free. Some comments with that though, you do have to have MATLAB. MATLAB
right.
is not free. So they do have, I think for for an individual hobbyist, I think they have MATLAB licenses that are somewhere around $500 or less. I think $250 for a non-commercial, like hobbyist type of MATLAB license.
Will it run on Octave?
It will not. We've had people try, and we've had people try as recently as like the HamSCI workshop, and the people that were trying, I think they were like blood relatives with the people who maintain Octave and things like that. So these were people who knew something that were trying. So we do have, there is an effort that's ongoing to port FarLab over to Python, and that is Bill Lyles and Josh Vega are making progress on that.
Very good. Good comments.
Mm-hmm. The other thing I wanted to say is, FarLab, one of the big differences is it really is geared toward more of a programmatic sort of use. So where I've never used PropLab Pro, but from what I understand, it's more of a GUI, graphical user interface sort of option. And FarLab is really designed to be, you write scripts and you use it more like in a programming language.
Right.
So it's more of an API. And that's how we used it for the 2017 Eclipse GRL. I actually had my undergrad student, Josh Vega. He was able to port it over to the NJIT supercomputer cluster. And then we ran lots and lots of ray traces using their cluster computer. I had a question, Carl.
Yes.
So it looks like PropLab Pro will calculate a path loss, a dB path loss for each path.
Yes. Yep.
Do you know what goes into that calculation, how it's done?
Probably I'm sure it's the equation for ionospheric absorption that you see in some of the technical literature.
Mhm.
The electron density, the collision frequency, and all that. So it goes through a rigorous calculation
Yeah.
as the wave progresses through the ionosphere.
I'd be curious to know more of how it does that. I don't think Farlap has a canned routine in there for doing that. I think they might have been adding it, but last time I think they've been working on it, or working on adding some, better absorption calculations in there. But I don't know what the status is on that.
Do you know if they, Farlap ports in MSys at all? Because if they port in MSys, they're probably solving the complex. And then that would give you absorption, complex Appleton-Hartree equation.
Yep.
I don't know if they're importing MSys or not.
Okay.
Yeah, because you can, in PropLab, you can tell what the collision frequency is, and it's usually broken up into 2 altitude regions for the lower ionosphere, and then for starting at 140 kilometers or so.
Mhm.
And you have to go find out what typical collision frequencies are for electrons and neutrals.
Yeah.
It's a rigorous calculation, and of course it depends solely on how good is the model.
Yeah.
And of course, down in the D region, our models are based on a lot less data than what we have for the F2 region and the E region. So,
Yeah.
yeah.
And that's one of the things that makes it so tricky. I think your comment on the IRI and the models that these things are using, they're all based on, monthly medians. And Phil Erickson keeps on, driving that point home. That doesn't really explain what's happening,
Yeah.
on a day-to-day or even an hour-to-hour or a, 10-minute to 10-minute basis. There's a lot of things that happen much faster than that, with much smaller, finer spatial resolution than
just as with normal propagation prediction programs like VOACAP or W6AL prop, these ray tracing programs allow you to see trends and not exactly what's happening right now, unfortunately, but maybe sometime in the future we'll have that.
Carl, could you go back to the ray trace that you made for Steve's station, please?
Okay.
Because I put in the chat window Farlap ray trace that I did for October.
Okay.
I have the code for that pretty well set up. So if anybody wants to see a ray trace for their station, just send me your latitude and longitude, and I'll send you a video. But I find it interesting because I'm looking at yours and I'm seeing many more modes than I see in mine. And I took the Farlap code and adapted it to figure out which rays are hitting the station, but I'm wondering if there's something else I should be doing. So maybe you could tell us a bit about these modes.
Well, it's at 5 megahertz. It's let's see, 1430 is probably around sunrise, and I'm not sure what else to say in comparison to what you did. It's somewhat of a short path too.
I think, Kristina, you've only been looking at one particular frequency, right?
The one that I sent has 5, 10, and 15, I think.
Okay.
Sorry, 2.5, 5, and 10.
So, Kristina, are you doing 2D or 3D?
2D.
2D, just like this, okay.
Yeah,
it's much quicker, of course.
I guess maybe it'd be, maybe Carl, would you mind reproducing Kristina's plots in PropLab Pro? So
I'd love to. Yes, I'd love to.
that way we could, compare apples to apples, because there's we're not sure that if you have the same parameters set for both ray traces.
And
it's for a different date for starters, but yeah, I'll shoot you guys an email and we can talk about it offline.
And of course, for what it's worth, PropLab uses, the 2007 version of IRI, and Farlap
This is
uses 20. Yeah,
16.
so, yeah, I don't know how much difference that makes, because I think most of the differences aren't due to, you know, FOF2 type issues and FOE and all that. It's all kinds of other peripheral stuff.
So in your chart here, one quick question on that. The 5 modes, you have 1E, 2E, 1F, 2F, and 3F. Does that mean that those are corresponding to, say, the, is that what layer, or is that just saying there's a there's 2 rays hitting the E layer and 3 rays hitting the F layer?
No, what 1E means, it's one hop and it gets up to the, only gets up to the E region.
That might be what's going on with mine, is I think I only looked at 1 hop.
Okay, and then, you know, 2F means that there's 2 hops, but they both get up to the F region altitudes.
All right, thank you.
You're welcome.
All right, thank you very much, Carl, and thank you, Kristina.
Okay,
That
let
was
me
an excellent presentation.
stop
We
sharing.
want to switch gears for a minute to something that is related. We have a second presentation today from Veronica. Are you there, Veronica?
Hello.
Hi, Veronica. So Veronica is she is a sophomore physics student at the University of Scranton. Her call sign is KD2UHN, and she will be talking to you today about a gap that we see in the propagation paths reported by RBN and WSPRnet. So take it away, Veronica.
Okie dokie. I'm gonna share my screen. Okay. Okay. So today I'm going to be giving a presentation on the investigation of gaps seen between 4,000 kilometers and 5,000 kilometers in reverse beacon network and WSPRnet amateur radio spot observations. So a brief introduction to what I will be talking about and just kind of some background is amateur or ham radio data can be collected through the reverse beacon network and the weak signal propagation reporter network. And these are both networks of stations that report contacts made by ham radio operators. The RBN and the WSPRnet are quasi-global, and the transmitters and receivers that they're picking up are concentrated in certain areas based on geography, population density, and demographics of different countries. So the question that we are looking to address in this presentation is, how does this distribution of stations affect the observations that are made by the RBN and the WSPRnet? So I have this graph. This is based off of actual data. And if you look on the left-hand side, this shows the midpoints between the real ham radio transmitters and receivers. And then on the right, this shows the distribution of the contacts picked up by the RBN and the WSPRnet. And on the left side of the figure, you can see it is labeled 20,000, 40,000, etc. These are the distances between the point of that the transmitter is at and the receiver is at. And you can see that in each of these images around 4,000 kilometers, horizontally, there's a gap that occurs on various different bands. And this is just one example from one day, but this is in practically every, all of the data that I've been looking at. This is in practically every one of these graphs. So the methodology that I use to address why we're seeing that gap in the data, a generic methodology is I generated theoretical points of contacts, and that these theoretical points are evenly spaced across the continental United States and Europe. And they were chosen because they are the location of a majority of actual radio operators picked up by the RBN and WSPRnet. And even though these locations are selected based on actual data, the points in this presentation are theoretical. So if you look at these images on the left-hand side, this is this is based on actual data. This was one of the distributions of stations, and you can see that a large portion of, this shows the midpoints between them, and you can see that a large portion of those stations are in North America and Europe. And on the right, this is the theoretical grid that I created, and the theoretical stations are concentrated in the same areas. And just again, these points are evenly spaced to show the probability density function of a particular distance showing up in the RBN and WSPRnet, assuming all of the United States and Europe have equal opportunity to talk to each other. So more specifically, I used Python to write a code, and the basis of my code was I imported libraries, so matplotlib, cartopply, harkplot, numpy, pandas, and itertools. I defined a range of latitude and longitudes that I would be generating the points in. So for Europe, I set those boundaries at 40 to 75 degrees latitude and -10 to 50 degrees longitude. And for the United States, I set the boundaries at 25 to 45 degrees latitude and -130 to -30 degrees longitude. And then I appended those latitude and longitude ranges to a list to make every combination of latitudes and longitudes within those ranges. So basically, what that's saying is I took each point and said what would happen if they contacted every other point on this theoretical grid. And then I used cartoppy to plot a figure that shows a map of the primary locations of ham radio operators. So again, these points are theoretical, but they're just distributed based on actual data. And then I generated these points every 10 degrees apart in that range and plotted them. So just to show, it's kind of the way the code is outputting, it's hard to see the individual points. So this is just a close-up. And you can see that I only included the points that were on land because a majority of, in like the real world application to this, you would find ham radio operators and receivers, a majority of them would be on land. So, but this is the points that I'm talking about when I say my theoretical points. So after that, I used itertools to create every possible combination of coordinate points. And then using vectorization and great circle distance, I calculated the distance between each point. And then I binged those calculations and I used those bins to create a histogram. And this is the histogram that shows the distance distribution of the United States and European theoretical locations. And you can see that on the y-axis, this shows the probability density. And on the x-axis, this shows the great circle distance. And around 4,000 kilometers, there's a significant dip in the graph. This is just a little bigger. There's the dip. And the ocean is roughly 4,950 kilometers wide. So that's around the same range we're seeing the dip in the histogram. And it would make sense that not as many midpoints of contact are located in the ocean. So therefore, undoubtedly a portion of the dip in the histogram can be attributed to the ocean. However, there's still a possibility that a portion of it can be attributed to other causes. For instance, the way that the radio waves are propagating with respect to the ionosphere. But basically a summary, just a recap of what I did was I was addressing the question of how does the distribution of stations affect the observations that are made by the RBN and the WSPRnet, because the RBN and WSPRnet amateur radio spots routinely show a gap between 4,000 and 5,000 kilometers in communications range. So I calculated the communication ranges between all the stations in a theoretical 10 degree by 10 degree latitude and longitude grid, distributed across the continental United States and Europe. And then I found these ranges have a bimodal distribution with a dip around 4,000 kilometers, suggesting that observed RBN and WSPRnet range gap is due to the geographic distribution of amateur radio stations. And then just a side by side, you can again see these horizontal gaps on the left-hand side that are around the 4,000 kilometers, which is roughly the same location we're seeing a dip in the histogram I generated for the theoretical points. Any questions?
Oh, good job. Good job.
Thank you.
Yeah, excellent.
Did you plot any histograms of the actual data in a histogram format? You have the nice 2D histograms. Did you try to summarize those into the kind that match your other plot?
I did not do that, but that is something I can look into doing.
Yeah, the question would be if the depth of the dip in your histogram from simulation looks sort of similar to the depth in the measured data. Very nice job.
Thank you.
That's a great idea, Tom, and we're looking for things to do next. So that sounds like a winner.
I like it.
Thank you.
Any other questions or suggestions on, did this bring up any more questions that you guys have? Where should we go next?
Perhaps I should. Let's see how to.
Yeah, we can hear you, David.
Okay, perhaps I'm misunderstanding, but it just occurred to me to wonder why the dip isn't bigger than it is. I mean, isn't deeper the valley there. I suspect my way of looking at it's probably not quite right, but you just to invert the question in a way, ask not why the gap is there, but why isn't it total, for say, but that may be.
My thinking on that would be because the graph is showing the midpoints between transmitters and receivers, and there still are some transmitters and receivers that can communicate across the ocean, but a majority of them are not doing that. So there's still going to be some points in like the location of the gap, which is why it wouldn't be deeper, but because a majority of them are not crossing the ocean, that's why we're still seeing that gap.
I guess that makes sense to me.
I think another way to think about it is, you know, if you ask yourself the question, if you're out of this ham radio, out of all these locations, how many possibilities are there for talking to someone, say 4,000 kilometers away, versus how many possibilities are there for talking to someone 1,000 kilometers away? So what Veronica's plot is really showing is that distribution. It's a probability, essentially a probability density function, saying that's calculated by figuring out, okay, how many, if you do the unnormalized probability density functions, it's how many paths have a distance of, say, 1,000 kilometers, 5,000 kilometers, 10,000 kilometers, etc. And so there are less options, there are less possible paths between 4,000 to 6,000 kilometers when looking at stations in the US and Europe versus those other distances.
Yeah, there are less, but not none.
That's right.
Yeah.
Not none. there are less. So, I mean, other things that
And
I've been
you
thinking
got to
of,
remember.
yeah.
Oops. You got to remember that some of those paths are north, south, east, west, northwest, southwest,
Mhm.
Of course,
northeast,
yeah.
southeast. So you can get
Exactly.
those distances.
Yeah,
Yeah.
that makes sense.
So
Yeah.
I think another thing to think of with this is, we've assumed a uniform distribution of ham radio operators every 10 degrees latitude and longitude across the US and Europe. And that's not true. that is definitely not true. And we've also, the other thing we haven't considered at all is things like skip distances. For different bands, we could go back to ray tracing and, monthly meetings and all that sort of stuff. And we could do a ray tracing study to see, okay, where is the one hop skip distance for different bands as a, function of like time of day. And that would also, I imagine that would also create a gap, but where it would be, would it fall at the same place? I think the F region, the F2 region maximum skip distance is somewhere around like 3,000 or 4,000 kilometers. And that's like assuming a F region altitude of something like 250 kilometers and a 0-degree takeoff angle. That's like the maximum distance you get from that. So that kind of falls, that one hop skip distance is actually at a very similar distance to this gap that Veronica is seeing. So it could be that you have both of those together.
Which makes me think that, for that next step where we were talking about doing this was the theoretical, and now we're going to look at the empirical distribution. You certainly want to look at it time of day. You want to look at it by band, maybe by season or something like that.
I think so. And I think this is also I think what we're doing here is really important work, because if we're going to be able to use RBN and WSPRnet and any of that sort of stuff in a scientific or space weather context, I think these are the sorts of data set peculiarities or biases we need to understand.
Very, very interesting.
We have a couple minutes left, and I just want to show one thing. This is very, 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 very early preliminary work that I just threw together, but I'm supposed to show it at the American Geophysical Union meeting in December. And I think I might have flashed it on the screen here before. So this is very unprocessed, very, very preliminary. But what you're looking at right here is essentially a solar cycle's worth of RBN and WSPR data. And so it starts in 2009 and goes up to 2020. And so if you weren't convinced about the gap that Veronica showed before, I think this will convince you, because here's 11 years worth of data, and every single band, 1.8 megahertz, 3.5, 7, 14, 21, 28, you see that gap for all 11 years. So I think that's pretty convincing. Well, any other final questions or comments before we close out today's Telecon?
Yeah, I'd like to bring up the ham radio buoy senior project, because there's a couple of students from that here, just for a moment.
Yeah, go ahead.
Quite a few people on this Telecon probably saw this on the list. We had a nice long discussion about if you were to put ham radio on an ocean-going buoy, what would you put on it? And we had a lot of excellent ideas come up about long-term things, and there's some interesting projects that we found out about that are happening now. But I'd like to give the students, we've got Miley's here, and then Lydia, I think, is the phone number that's called in, some guidance about what payload they should put on their prototypes for this semester. So I was wondering if people have any thoughts about WSPR versus APRS versus something else, and sort of what sort of antenna would be best.
Well, my experience with WSPR is that it's pretty darn incredible in terms of propagation. I run 200 milliwatts with a wire literally lying on top of the grass in my backyard and get over the pond on a regular basis. So anecdotal, not scientific, but I'm just absolutely impressed with it. And there's also now, I'm not sure how you would do it, but there's this FT4 mode that just came out. And it's one, go on Joe Taylor's website. There's a new FT4 that's part of WJST, but maybe there's something that some way to run it independently. But it's supposed to get down to minus 30, minus 33 dB or something, which, yeah, it's would be pretty incredible.
FT4 is a shorter version of FT8, so it's not as robust as FT8 is, and in turn, not as robust as Whisper is.
Right.
Okay.
As far as antennas go, Zach did some pretty good work on developing a wideband omnidirectional antenna. So you might want to look into the documents that he posted. They're in the HamSCI archives. But just to get started, if you're talking about ham band only, you can get a multiband vertical for cheap and put that up like an old Hustler 6 BTV will work just fine. Or one of the DX Engineering whips that's more or less optimized for low bands, but the ARAV4-1P is what we're using for the RBN nodes that are being shipped out all over the place to Russia and the Caribbean. That antenna is about 300 and something, close to $400. It comes with the amplifier and all that kind of stuff. But there's a lot of used antennas out there for the ham bands that you can get for considerably cheaper. I don't know what your budget is.
Well, also single band antennas like Fire Sticks and things like that, while less than optimum, they're incredibly cheap and they're encased in PVC. So for putting out in an ocean going buoy, they probably would outlast something like a 6 BTV or something that has bare aluminum. And I think the less than 0 dB noise floor modes on HF are a great addition to a buoy like that, especially with subpar antennas and really low power. And like Bob said, you can really get good results with less than a watt and not very much of an antenna. And especially you're going to be over salt water. So.
Yeah, I'm embarrassed. I forgot you were talking about the buoy. Yeah, you don't want to put a trap vertical out there.
Well, that was my follow-up question was, is it waterproof?
No. I think a total wire-wound helical antenna would be what you want, not even with a whip. You'd want the whole thing encased in plastic, and then they have the stainless steel bushing down at the bottom that you can mount and attach firmly and then seal with a conformal coat of some sort. Thanks, Scotty.
And you can buy those coated encapsulated stainless steel whips really inexpensively at flea markets. You can buy them even new at the flea markets for 20 or 30 bucks. And like HRO has them, they're considerably less than the base station antennas. So yeah, that probably would be a good choice.
And I put in the comments Zach Tech. He's an amateur in Sweden who has been shipping a well-regarded line of multiband Whisper transmitters. I have one on order. I'm expecting it shortly. I'll be using it on 30 meters as the back survey for my 10 megahertz WWV monitoring.
You can also get this marine epoxy that you can encase things in, and it's pretty impregnable once you get it mixed up and the stuff dipped into it.
One thing is interesting is Tapper sells a Whisper board also. It's not a complete transmitter like the Zactec stuff, but we've actually tested the Whisper transmitter board on a Raspberry Pi Zero. So it really doesn't take much of a computer at all to run it. So if that's in the power budget and the weight budget and the dollar budget,
that might be an alternative. I don't know what the Zactec ones cost, whether they're cheaper than a Pi plus a half, or whether they aren't.
Well, one question I have, if David's ordered one of these, is what's the turnaround time like?
I put in the order about 10 days ago. I'm expecting it soon. And I did send an email to him asking how well he'd be able to supply them in quantity for the WWV work. So I'll let you know, or you can take mine.
I want to take your stuff. Looks like they're, let's see. I can't find a price on the mini. I see that the Tapper one is 32 a piece.
And then a Pi Zero is another probably $10.
Like 10, yeah.
Yeah.
I think that's pretty
We're just
reasonable. We
gonna-
are looking for something COTS. I think Lydia was going to say something. Lydia? Maybe not?
I was just going to, sorry, I was going to ask for the name again, but Tapper is what I should look for? T-A-P-R?
Yeah, I'll send you these links.
Leaderboard?
I'll send you the links
Great.
for these.
How many buoys are they planning on putting out?
So this is just a little pilot project for a MECI senior project, but hopefully one in Lake Erie and one in Bermuda. So that's where the students are. There's 2 in Cleveland, and Lydia is far away.
Okay.
60 miles south of Bermuda.
Yep. Is that where you are right now?
Yes.
So, yeah, so supply chains are long and hard to maintain, and we're looking for keeping things simple so that we can get something that's, you know, waterproof and can be put in the water and will give us something to get started. Whether that becomes a larger HamSCI project in the future, I don't know. I think it might have potential to, but right now we just want to get something in the water. So, and because they are approaching this as a MECI senior project, electronics are not really too much in the scope. Hooking something up is fine, but I don't want them to have to get too deep into that part of the project because it's not really what their focus is. So these Whisper boards look like a good approach. Anything else we should be considering? Any other modes?
How long are you planning to let them run for?
As long as they last. The pilot one out of San Diego that gave us the idea for this project was meant to last 6 months and died after about a week, which honestly I think is pretty good for something that you throw into the Pacific Ocean. Yeah.
So you're not necessarily, or are you trying to get into like solar power and recharging and all that, or are you just looking to big battery, throw it out there and see how long it lasts?
I'm thinking big battery for the first round, but I'll leave it to the students.
We are looking into doing solar power or wave power or wind power, but that would be probably like further down the line. For this, it's probably just put a large battery in it and maybe think about starting to get renewable power and throw it out and see if it lasts long enough that it's worthwhile to go as an alternative power source.
Okay, yeah, I guess the reason I was asking is if it's solely battery powered, then eventually we know it'll turn off. But if you wanted to go for longer, having that positive control of the transmitter, that's where on the list I chimed up about like Iridium modems for the command and control and maybe like very short text message backhaul. But that's a whole to-do to get the like API up and running to interface with whatever service provider and all that kind of stuff. So I'm not sure I have a good idea to answer your fast question there. Just chiming in about that. The other thing I'll mention, I know you kind of already shot this down, but you can also build Whisper transmitters really easily out of Arduinos now with an SI5351 chip. And there's like 14 different example of code bases out there for that. So that's just another option to throw out for kind of low power alternatives. It does need filtering on that chip though.
All right, I'll add that one to the list. I see it's really easy to find project pages for it, so It's an option.
Kristina,
Yeah.
how far, do you know how far off the Pacific coast the one was launched?
The original.
Yeah.
Let's see.
The reason I'm saying that is I don't know where you're planning on launching, but boy, if you can catch, I suspect the one on the Pacific coast wound up destroyed on the coast.
Well, theirs was deployed at the coordinates that I'm about to stick into the chat by a research vessel.
Oh, okay, so it was
yeah,
offshore.
So they didn't throw it in from the shore. It's on KQ6RS's QRZ page. He's got a little section on it at the end, and he's been in touch with the team and offering documentation and things.
Yeah, I'm just curious to know what current they were trying to catch. I mean, off the East Coast, you could easily catch the Gulf Stream and have it go all the way across. I mean, right off the, I mean, barely a mile off the coast of Florida, you can catch the Gulf Stream, and get it all the way across the pond.
The best guess that anybody seems to have for how this one died was that the antenna might have snapped off and there was water infiltration, but there's not enough. All you have is a flat line. Like, you don't know exactly what it was that did it. So
yeah.
Could be sea monsters.
I know of at least one auroral acceleration paper that was published by Hallinan et al. That actually had a sea monster in the figure. I can send you the reference if you want.
Yes, please.
Okay.
All right. Well,
you can do that. You can do that once you become famous and you're emeritus. Then you can publish
whatever
space
you
physics
want.
papers with sea monsters in them. But you can't do that early in your career.
I was gonna say you can do that anytime, just not in very many journals.
Right.
All right. Cool. Let's see. So so we'll probably look at the whisper beacons. And any antenna thoughts on that are always welcome. But probably one of those whisper boards that we looked at here will be the main payload then.
By the way, that Latin Long is about 800 miles west-southwest of LA. So
wow.
Good ways out.
Mm-hmm.
Humboldt current.
And
right.
Nathaniel, I just got an email from the CM. The first 5 magnetometer boards are ready for pickup.
Fantastic.
So
that is great.
I know what I'm doing this weekend.
You're going to be busy.
Yeah.
Okay, here's the, for anyone who wants that article with the sea monster in it, I put the link in there. I think it's behind a paywall, so you probably have to consult with your local library, or talk to someone, or but there's the main link, and I'm trying to find wanted to get, and the figure you are interested in is yes, figure 10. So you want figure 10.
Figure 10. Thank you.
Yes.
All right.
Figure
Thanks,
10.
everyone.
Okay. So I think that will wrap it up for today. I do want to say that we don't have any speaker yet for October 15th. Would anyone like to volunteer to give a presentation October 15th? I will put that request out on the list again. For October 29th and November 12th, we do have a speaker, and that's going to be Ben Vitfleet. So you can see, where'd it go? I shared my screen, it disappeared. Sorry. Right, so on October 29th, Ben is going to present on near vertical incident skywave propagation rather. And this actually will tie in nicely with what Carl showed today, because Ben did an extensive study looking at O and X mode polarization, and he has something called the happy hour propagation interval, where you can actually separate out whether you're hearing O or X mode. So he'll talk about that on that day. And then on November 12th, Ben will be back, and he will be talking about measuring radio noise. So those are things coming up on October 29th and on November 12th. And then tonight is October 1st. There is a full moon and a harvest moon this evening. So you might want to check your local moon rise times. And tonight is a great night to see that, because also later in this month, October 31st, will be the second full moon of the month, which makes it a blue moon. And that will be on Halloween. So if you want to catch both full moons this month, tonight, October 1st, and then again on Halloween. All right, I think that's about it. Thank you very much, everyone, and we will talk to you soon. 73.
Thank you, Carl. Thank you, Veronica.
73.
Yeah, great job,
73.
everybody.
Thank you, guys.
See ya.